Okay. Hello, good morning. Very good day to all of you. And are you able to see the slides?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Here we are. Department of Chemical Engineering, Manasthali Vidyapeeth welcomes you all. And there we are on CHT 305 Chemical Technology. We are on lecture number 4. This figure shows you an anatomy of a chemical process. See, in any chemical process, you have raw material and then product. Now, the raw material is stored, that is stage 1, raw material storage. Then the raw material may not be in the form by which the reaction takes place. For example, it may be a hard rock. You have to, not hard rock cafe, right? Maybe a very hard rock material which you have to crush, pulverize, and make it into a fine powder. That's all we call it as feed preparation. It may be that raw material is cooled, you have to heat it up. Raw material is at one pressure, you have to increase the pressure. So this is what is the feed preparation or stage 2. Stage 1 is raw material storage. Stage 2 is feed preparation. Don't look at the back arrow. Let's go forward. Feed preparation. Then when the raw material is ready as feed, then we put it into the stage 3 where the reaction takes place. And after the reaction, the product is formed. Product separation takes place. And the separated product goes for purification because there may be some impurities in the product which has to be purified. That is stage 5. And stage 6, product storage and sales and marketing and bank balance. Right. Then in the product separation, we separate the product and also unreacted raw material. The unreacted raw material, I don't want to throw it. I would like to recycle them back. And if my reaction is not efficient, some byproducts may be formed. So the byproducts have to be removed. And in addition, some waste may be there also. That is the byproduct means it is not your main product, but a product which is still of some use. Waste means good for nothing. So it has to be disposed of, right? And the purification also may produce some waste, which is all, tucked away as waste. Remember, this is the typical anatomy of any chemical process. So any process can be simplified in this diagram, right? Of course, the reaction may not be just one box. There may be several reaction, then something, then again reaction. So this box may get blown up. Okay, and in recycle, it may not be as simple. If some inert material is present in the recycle, you may have to do a purging operation, which you have studied in your chemical process calculation, like removing the argon, etc. in the recycle for nitrogen and hydrogen. All processes typically have a raw material purification and preparation stage and product separation stage. That's what we just saw. Raw material preparation and product purification stage, right? And example, zinc and lead milling and beneficiation process for zinc and lead ore from mine. Of course, this is only an example. Almost every process, some purification and preparation will be required. When it comes to choosing between the raw material may be wet, you may have to dry it because the reaction takes place in dry condition. So raw material preparation could be as simple as a drying operation where the moisture is driven away. Right. When it comes to choosing between a batch process and continuous process, you know the difference. Batch process, soup making, right? So where you add, all the component for making soup, keep it close, and then after the required time, pull it out and sip the soup, right? Continuous process means continuously you are adding raw materials and continuously you are getting product, right? So, and in between there is a semi-batch also where raw material is not added all in one stage, but in with certain intervals, okay? But product is not continuously withdrawn, right? Batch process preference is always given for continuous process because in continuous process, the steady state operation, material coming in and going out, and designing and controlling the process becomes easy. But batch process, remember, initially the concentration of raw material will be high, then it starts decreasing, and the product concentration increases. Then this is not uniform like the continuous process. So designing and controlling a batch process poses certain extra challenges as compared to continuous processes. So more batch processes are being converted into continuous processes. Okay, but still there are some chemicals which can be made only by batch process. Okay, coal handling plant. Remember, the overall process may be continuous while parts of the process may be batch. This is interesting. For example, a thermal power station which uses coal as the fuel is a 24 by 7 operation. It is continuous operation. But whereas the coal handling plant in the power plant is not a continuous process. The coal handling plant may operate one shift or two shift depending upon whether how much space you have. If you have a lot of space, then one shift operation is enough. And if the storage space is little, then two shift coal handling plant is run. The reason being, coal handling plant crushes coal and subject to failure every now and then. So it requires maintenance and overhauling, right? So running the coal handling plant on a 24 by 7 basis becomes difficult because if the mill breaks, then the entire plant has to shut down. If the coal handling plant has a breakdown, then the entire power plant has to be shut down, right? So one way is, I have a spare coal mill, but coal mills cost, crores of rupees. So it's not economical to duplicate. So it is usually run in one shift or two shift, and storage takes care so that one or two shift is available for maintenance and repair purposes of the coal handling plant. Now, steps in process synthesis. When I say process synthesis, it means designing the process from the raw material to the product stage. And when I do that, then I have my process synthesized or my flow sheet is ready. Okay, there are four steps: alternate reaction paths, species allocation, separation task selection, and task integration. Okay, now alternate reaction paths. Remember, every chemical, right? Almost everything in life has more than one way of doing. Remember, you want to come from Jaipur to Banastali, you can come, via Chaksu or bypass Chaksu and come in the bypass. Both ways you reach. So similarly, for making any chemical, there is more than one way of doing it, right? So invariably, every chemical has alternate ways. So finding the alternatives and choosing the best, that is the first step in process synthesis. And creative part of process synthesis is looking at the target molecule. We should be able to work backwards to reach the raw material. For example, if you say the product is Na2CO3, sodium carbonate, you know that looking at the product, there must be a raw material which has sodium and raw material which has carbonate. Then only sodium carbonate can be formed. And it is common sense that the most abundant material available on earth containing sodium is seawater, sodium chloride, right? So NaCl is the source for making Na2CO3, and carbonate typically comes from calcium carbonate because limestone is another abundantly available, right? So I am giving this example to do the looking at the target molecule because this is how pharmaceutical parts are worked out. So a target molecule is considered and which will have the required medicinal effect, bring the cure, and looking at the target molecule, then precursor to the target molecule is found, then precursor to precursor, precursor to precursor, precursor to precursor, until you reach raw material. Okay, so that is how it is done. Okay, so let's have a look at it. To understand reaction path synthesis, the most classic example of reaction path synthesis is vinyl chloride, CH2CHCl. Wow, what a simple chemical, but let's see the challenges in making this vinyl chloride. See, we know methane, ethane, propane, butane, they are all hydrocarbons. But why do we chlorinate a hydrocarbon? Chlorinating hydrocarbon is the basic idea behind the production of vinyl chloride monomer. So you can see that we are just say ethane molecule, we are doing some change and getting into CH2CHCl, or we have ethylene molecule, and ethylene we are somehow uh, putting a Cl into the ethylene molecule. So by looking at the product, we are able to look at it, right? So CH2CHCl, which means ethylene or ethane could be a raw material for it, and we should be able to do the job, right? Or two carbon acetylene is also there. See, looking at the product, you should be able to mentally find out what could be the raw material. So two carbon, so maybe ethane is the raw material, and or ethylene is the raw material, CH2 double bond CH2, right? Or acetylene is also a possibility, CH triple bond CH. Okay, so using that and chlorine, we should be able to make this. So chlorinating hydrocarbon is the all are hydrocarbon, acetylene, ethylene, ethane, all are hydrocarbon. Okay, chlorinating hydrocarbon is the basic idea behind production of vinyl chloride monomer. Right, this is known as vinyl chloride monomer or VCM. Right, chlorinated hydrocarbons are much more resilient to biodegradation. Right, see the normal hydrocarbon is capable of getting biodegraded, but the chlorinated hydrocarbon is not ready to undergo biodegradation. Okay, and we know it. That is how we made the ozone problem, right? So it's a very well-known thing. Unlike simple hydrocarbon, the chlorinated hydrocarbon are more resilient to biodegradation. This is due to mainly why it is so is, see, compared to the carbon hydrogen bond, the carbon chlorine bond is strong. तोड़ना मुश्किल है, that is why बैठ जाता है, right? Consequently, man-made chlorinated hydrocarbon CH3s are beginning to accumulate in the environment. Let's not get into the ozone hole, right? It is a well-known disaster, and we are all recovering from that for having made whole lot of fluorinated hydrocarbon, right? CFCs, right? Then, however, production of vinyl chloride monomer uh, is essential for production of polyvinyl chloride. Polyvinyl chloride construction materials made of PVC are light, low maintenance, long lasting. PVC products are highly resistant to weathering, can withstand summer, winter, petroleum product, and UV radiation. So PVC is a good product as far as utilization is concerned. So we would like to do it. PVC is flame resistant also. It's been extensively examined in regard to fire prevention, and there are so many positive aspects of using PVC that it is imperative that it be produced. So to make PVC, that is polyvinyl chloride, I need the monomer VCM, vinyl chloride monomer, right? Many, however, what is the problem is when I produce VCM, I produce some more unwanted chlorinated hydrocarbon, right? And which is of growing concern. Therefore, VCM vinyl chloride monomer must be produced in a way that will minimize or totally eliminate the release of CHCs into the environment. Okay, so look at the next step. Alternate path for vinyl chloride manufacture. Vinyl chloride formula is CH2CHCl. It was first produced using the process of dehydrating ethylene dichloride, EDC, right? EDC is say you can say dichloroethane over ethane. You have replaced two hydrogen by two chlorine. Okay, by dehydrating ethylene dichloride with alcoholic caustic potash. This was the earliest processes for making vinyl chloride. However, the first effective industrial process was based on hydrochlorination of acetylene. Right, acetylene, you know, is CH triple bond 3CH. Right, you add HCl to it, and hydrogen and chlorine move over to one of the double bond, and you form CH2CHCl. Right, so but how do you produce acetylene? Acetylene is not readily available. Acetylene is made by from calcium carbide, CaC2, and calcium carbide with water forms acetylene, right? So, but making calcium carbide is again a very high energy requirement process, right? So remember, you can make acetylene when you make the raw material for acetylene, calcium carbide, because acetylene is not readily available, and calcium carbide is also not readily available. So try to convert the calcium carbonate into calcium carbide. It's a very high energy requirement, right? Removing the carbon CO3 and replacing it by C, right? So the very high energy process. So making calcium carbide is costly. Then because of that, acetylene is higher cost, right, as compared to maybe the other raw material, right? However, as ethylene became a more plentiful in the 50s, with refineries, ethylene started coming. Commercial processes were developed to produce vinyl chloride from chlorine and ethylene, right? So chlorine and ethylene can react to form what is known as EDC, right? Ethylene dichloride, right? And the balanced ethylene route. This is another one. We will see it. And today the balanced ethylene is responsible for well over 90% of world vinyl chloride production. This process has been refined and the scale of operation has greatly increased, but no fundamentally new processes have achieved commercial viability. Although this is true, it is still necessary. So we are now seeing that there is a way of making vinyl chloride starting with acetylene or starting with ethylene. All current production plants for vinyl chloride depending upon the use of C2 hydrocarbon. C2 hydrocarbon maybe acetylene, ethylene or ethane, right? Commercial operation using these compounds are confined to gas phase processes. All the reactions are happening in gas phase. Manufacture from acetylene is relatively simple because acetylene with HCl, you get vinyl chloride monomer, right? But cost of acetylene is high. Ethane is by far the least expensive because ethane is available in natural gas itself. Some ethane is there. Ethane is the least expensive C2 hydrocarbon. C2 means two carbon hydrocarbon, but it cannot be converted to vinyl chloride with high selectivity. See, if you take ethane and put chlorine on it, you get monochloro, dichloro, trichloro, all hydrogen, you know, there is no selectivity. See, we just want one chlorine to go and sit in the C2, right? Just one chlorine. We don't want all chlorine. But with ethane, you have a problem. So you get all sorts of products. So selectivity of making that monochloroethane is quite difficult. So that is where we are stuck. Okay. So vinyl chloride from acetylene. The process that produces vinyl chloride from acetylene employs the use of a catalyst. Right. So vinyl chloride, acetylene with HCl form vinyl chloride. Okay. Acetylene with HCl form vinyl chloride. But you need a catalyst, and the catalyst is mercury chloride. Another headache. Mercury chloride. Mercury is poisonous. Mercury chloride is more poisonous. Right. And mercury chloride deposited on active carbon. Okay, this is the catalyst. So in this process, the feed gas is purified, dried, and mixed at the entrance of a tubular thick bed reactor, which is packed with mercury chloride on active carbon pellets as catalyst. Right. Usually a slight excess of HCl is used over stoichiometry. You know the limiting reactant and excess reactant. And here normally HCl is used as the, remember, HCl is cheap. So you ensure that all acetylene is finished. That is, acetylene is more expensive, right? So it is will be the limiting reactant, and HCl will be the excess reactant, right? 99% conversion of acetylene and 98% conversion of HCl is achieved. Selectivity to vinyl chloride is good, more than 98%. The only significant side reaction is further addition of HCl to vinyl chloride to form. So one problem that can come is you form vinyl chloride, but HCl may, may become friendly with vinyl chloride and start reacting and make 1,1-dichloroethane, right? So dichloroethane, right? So this is the problem which has to be minimized. That is, you don't want the HCl to react with vinyl chloride product that is formed. Okay. The major issue with this process is the catalyst used is mercury chloride, the very volatile compound and also poisonous. It is so volatile that much of the development of the work on this process has been devoted just to the volatility of mercury chloride. Consequently, the acetylene route is currently of little commercial importance, right? So the acetylene route is as good as, not in use. Then comes the possibility how to make ethane, vinyl chloride from ethane. Remember, I told you that you can make vinyl chloride with acetylene or ethane or ethylene. We saw the problems with vinyl chloride.
एक पॉइंटर है, इसको यूज कर सकते हैं, ये हाइलाइटर है, ये फ्रंट टिप पेन, एरो, इसको यूज
Okay. Okay, so we can make vinyl chloride from ethane. Many attempts have been made to develop a process that will use ethane to directly produce vinyl chloride. This is because ethane is less inexpensive. The major problem associated with use of ethane is the molecular symmetry. Right? Remember, ethane, very nice, CH3, CH3. With one carbon, three hydrogen, with other carbon, three hydrogen, ekdam, symmetrically structure and properties of material, bad gas. So in particular, the addition of chlorine to ethane gives rise to a wide product spectrum. So the chlorine is the no selectivity. It may go and pick up any hydrogen, right? In fact, all the hydrogen also. The most promising route appears to be based on high temperature oxychlorination. Still, research work is on progress to use ethane as the better raw material even compared to ethylene. But problems have not yet been overcome. Okay. Okay. The ethylene may be chlorinated. Where is this? The ethylene may be chlorinated to EDC. That is, I have ethylene, CH2 double bond CH2. I add chlorine, and the chlorine, goes and sits on each side of the double bond. So you get dichloroethane or ethylene dichloride, EDC, and it is and ethylene dichloride on heating will form vinyl chloride and release the HCl. Okay. Although possible, this process has not progressed beyond the conceptual stage. This is due to the fact that oxychlorination reactor design presents a severe challenge in terms of materials of construction. Remember, with ethylene, what is the story? Just recollect. Ethylene plus chlorine forms the ethylene plus chlorine form ethylene dichloride. Okay, because both the chlorine have come and you heat the ethylene dichloride, you get vinyl chloride monomer plus HCl. Okay, that is how it is there. But every monomer of vinyl chloride you are producing a HCl. And what do you do with the HCl? The oxychlorination process is, something which looks at HCl and, makes chlorine from HCl. Okay, so remember, HCl is a useless product. Now, every vinyl chloride monomer, if I am producing one useful product with one useless product, then what do I do with the useless product? I can't just throw it, right? So it would be better that if I can generate chlorine out of HCl so that my chlorination of ethylene can take place. So that is how this oxychlorination reactor has come. And here the reaction may go up to 500 degrees centigrade, but at this temperature, chlorine becomes very aggressive to most construction materials. 500 degrees, chlorine becomes hyperactive. Okay, so we have a whole lot of problems, right? With ethane, ethylene, and acetylene. Finally, let's come to vinyl chloride from ethylene. Right? Ethylene can be converted to vinyl chloride in a single stage without isolating the intermediate ethylene dichloride by either chlorination or oxychlorination route. And the case, this is known as the balanced ethylene route. Right? Direct chlorination routes require a high temperature and large excess of ethylene to minimize soot formation. That is, soot is fine deposits of carbon. Substantial amounts of vinyl chloride are formed when the oxychlorination reactor is operated above 350 degrees centigrade. The common problem with the direct routes of production are poor selectivity to vinyl chloride. Just imagine one small chemical vinyl chloride with so many reaction paths are coming into picture. That is what you must get into your head. And each process has separate issues, cost, operating, selectivity, etc. This has substantially hindered the industrial applications of direct conversion processes. Now, we look at what is known as the balance process, which combines some of the reactions to our advantage, right? So, the process chosen for vinyl chloride production, the combination of two, both direct chlorination and oxychlorination. We'll just see what is oxychlorination. This process is referred as a balance process. So, what is balance process? It combines direct chlorination and oxychlorination. Direct chlorination by itself is a process that operates at lower temperature and produces fewer byproducts when compared to oxychlorination. But oxychlorination is used in vinyl chloride production because it consumes the hydrochloric acid. Remember, the chlorination route produces the HCl, right? And the major product of vinyl chloride production, the HCl is also produced. Currently, 95% of world supply is produced using the balance process. The main reaction in these processes are direct chlorination. This is the ethylene, CH2 double bond, CH2 plus chlorine. One chlorine will sit on each side of the double bond and you get, this is dichloroethane, right? Or ethylene dichloride. Let's put it, ethylene dichloride. Oxychlorination. Oxychlorination is ethylene plus HCl plus oxygen forms this ethylene dichloride plus water, right? So oxychlorination is using HCl and oxygen over ethylene. Then EDC pyrolysis. Pyrolysis is what? By application of heat, you are breaking the chemical. And so this is your dichloroethylene, right? ClCH2CH2Cl. This on heating gives you vinyl chloride and HCl. Remember, in the direct chlorination route, ethylene and chlorine form dichloroethylene, right? And the dichloro, right, on heating gives you your vinyl chloride monomer and HCl, and oxychlorination is using HCl and oxygen. Of course, oxygen is coming in the form of air, not as pure oxygen, right? You form again the dichloroethane. Okay, so or ethylene dichloride. Okay, be clear about the nomenclature. Now you add all the three reactions. The overall reaction is HCl gets eliminated. It is there inside, but gets eliminated because in one place it is produced, one place it is consumed. Okay, so two molecules of ethylene plus chlorine plus half oxygen produces two molecules of vinyl chloride monomer plus H2O. Okay, so more, this is a very vinyl chloride reaction is something over which whole lot of research and development work continues to go on. If you want to read more about it, the reference I have given in this slide, you could click and go through. Then come, we look at another MCD, monochlorodecaine. What is so great about MCD? MCD is used for detergent manufacture. Chlorinated decanes are used heavily in the manufacture of detergent. Right. It is desired to set up a process for the manufacture of monochlorodecaine from readily available. Remember, methane, ethane, propane, pentane, butane, pentane, hexane, septane, octane is 8, nonane, and decane. Decane is 10 carbon hydrocarbon, right? And what is the formula? CnH2n plus 2. So C10 H2n plus 2, C10 H22. That is, hydrogen is twice the carbon plus 2. Methane is 1 carbon, 4 hydrogen. Oh, why? Right, so plus 2, right? Cn H2n plus 2, okay? So decane is C10H22 reacted with chlorine, it forms monochlorodecaine. One chlorine goes and sits and one chlorine replaces the hydrogen, the substitution reaction, and the hydrogen that is removed combines with the other chlorine to form HCl. This is monochlorodecaine. And this is what is our desired product. But life is not as simple. As soon as monochlorodecaine is formed, it is capable of reacting with the chlorine to form dichlorodecaine and produce another HCl. And forget it, dichloro can react with chlorine to form trichloro, and you had it. Okay. Whereas our desired product is just monochlorodecaine. So this is path 1. Now you know, if I have to produce this, I will have to find a method by which this is just a photocatalytic reaction. Just in the presence of light, the decane can react with chlorine. But this is not selective because it can further become DCD, TCD, and as many chlorine as possible. Right? The ratio of DCD to MCD in the reaction is 1:4. Remember, dichlorodecaine, every 4 moles of monochloro, at least 1 dichloro is produced. Right? Second path, decene. Decene is the alkene of decane. Right? Like ethane, ethylene, decene. Right? C10H20. Right? Plus HCl. So this form hydrogen and chlorine add here and form C10H21Cl. There's a catalyst required for this. Right? Remember, the unsaturated hydrocarbons by chemistry, they prefer to undergo addition reaction. And straight chain normal hydrocarbons prefer substitution reaction. These are things which you have studied, let's say in Morrison and Boyd in organic chemistry. Right? Substitution reactions and addition reactions. And we make heavy use of them in our chemical technology. Okay. So decane with HCl can form monochlorodecaine, but a catalyst is required. And the third path is decanol. That is the alcohol of decane. With HCl can also form monochlorodecaine and water. Right? So you have 3 paths. Now, vinyl chloride, we had path from acetylene, we had path from ethane, we had path from ethylene, And in ethylene also, we made some modification using oxychlorination to get rid of the HCl. See, the field is challenging. Every product, there will be multiple paths. Now look at this. Having understood the same, now let's look at, let's say you want to make sulfur dioxide. Now let's mentally try to work out what are the alternate reaction paths. Sulfur dioxide I can make using burning sulfur, right? I have sulfur raw material, sulfur with oxygen forms sulfur dioxide. Roasting of pyrite ores. What is pyrite ore? Many minerals are available as sulfide ores. They are known as pyrite ores, like zinc sulfide, iron sulfide, lead sulfide. So they are available as sulfide ores. So when I roast the sulfide ore, that is known as pyrite ore. See, pyrite is a special name for mineral containing sulfur compound. Okay, so when I roast the pyrite ore, I will be releasing the sulfur as sulfur dioxide. So remember, our product is sulfur dioxide. So I can make by burning raw sulfur or by roasting pyrite. Of course, the purity of sulfur dioxide by roasting pyrite will not be good because it comes as a mineral product. So there may be a lot of impurities along with the sulfur dioxide. Whereas the purity of sulfur dioxide by burning sulfur, pure sulfur, sulfur is almost 99.9 pure available. So you will get sulfur dioxide which is very pure. There are many coals which contain sulfur. In India, it is said that the coal in Assam contains a lot of sulfur. Right? Purnima Mundra can check that up about coal in Assam. Right? So when you burn coal containing high quantity of sulfur, the sulfur burns to form sulfur dioxide. So sulfur dioxide can be produced by burning coal. Right? Wow. From hydrogen sulfide. In the petroleum industry, hydrogen sulfide is widely available as a byproduct because the crude oil contains sulfur, and in the refinery, hydrogen gets produced. The hydrogen combines with sulfur in crude oil to form hydrogen sulfide. Hydrogen sulfide, remember that famous rotten egg smell, right? I can use hydrogen sulfide using some oxygen reaction to form sulfur dioxide. So I have so many options. And remember, just sulfur dioxide can be produced by burning sulfur, roasting pyrites 2, combustion of high sulfur coal 3, hydrogen sulfide as raw material 4, and each of them has its own advantage and disadvantage. Right? One must screen each reaction path against various criteria for selecting the best reaction path. Right? Cost of raw material, cost of product, purity of product, all this must be kept in mind, and I may do a production consumption analysis to see the economics of the reaction path. Right? Remember, read this example. This is for making sodium carbonate. Now, I am not writing the reaction because you know it, but I'll just tell that sodium chloride plus calcium carbonate, NaCl plus CaCO3 forms Na2CO3 plus calcium chloride. That is the main reaction. Okay. Now, since Na2CO3 contains, you balance the reaction, then it becomes 2 NaCl plus calcium carbonate plus 2 NaCl plus 1 calcium carbonate, you form Na2CO3 plus calcium chloride. Okay, so now you know the reaction. Now assume the cost of calcium carbonate molecular weight 100 is $15 per ton. Sodium chloride molecular weight 58 is $20 per ton, and cost of sodium carbonate molecular weight 106 is $40 per ton. Right? See, you may mentally say, sir, sodium chloride is 15 and what is this? So calcium carbonate is 15 and sodium chloride is 20. So 20 plus 35 is 35 and sodium carbonate price is 40. So 40 minus 35, $5. That's not the way to calculate. That's not a way to calculate because molecular weights have come into picture, chemical process calculation. So I will have to do, 100 into 15 because one molecule of calcium carbonate, molecular weight 100, 100 into 15 plus two molecules of sodium chloride, 2 into 58 into 20. That will be the cost of raw material. So 100 into 15 plus 2, because in the balanced equation you have 2 NaCl. So 100 into 15 plus 2 into 58 into 20. That is the cost of raw material. And the product will be one molecule of sodium carbonate, 106 into 40. Right? So now you do 106 product cost minus raw material cost. So 106 into 40 minus 100 into 15 minus 2 into 58 into 20. Then you will get a value divided by the molecular weight of 106 sodium carbonate, you will come to $4 per ton, right? So this is your calculation. 20 plus 15, 35, 40 minus 15 minus 20 is not correct, right? You must use the molecular weight to do your chemical process calculation, right? So that comes to $4 per ton. But remember, this doesn't mean it is profitable because you have to have operating costs and other expenses. They all have to be added, right? It is only giving a quick estimate of the consumption of the reaction with product cost and raw material cost gives you initial profitability prospect of the process. Then the next step is species allocation. Species allocation means, remember, when we talked about the sulfur dioxide, the roasting of pyrite, it will produce the impure sulfur dioxide. And combustion of high sulfur containing coal, also the product sulfur dioxide may not be pure. Hydrogen sulfide to sulfur dioxide, the process is not highly efficient, right? So, in fact, you may have to convert hydrogen sulfide to sulfur and then burn sulfur again to form with oxygen to form sulfur dioxide. So the most robust way of making sulfur dioxide is by burning sulfur. So assume that we have screened qualitatively to choose the burning of sulfur as the best alternative for reaction path. Sulfur plus oxygen forms sulfur dioxide. Sulfur is a species. Oxygen is a species. Sulfur dioxide is a species. Now, species allocation means where do I put each species in my process? Okay. Now, we will try to analyze this quickly. Okay. Now, let's come. This is a sulfur burner. It doesn't need catalyst. All I have to do is burn sulfur, and let's say I take 100 moles of sulfur and put it in the burner, and I need, as per stoichiometry, as much sulfur, as much oxygen. So I need 100 moles of oxygen. Where do I get oxygen from? I get oxygen from air. And air contains nitrogen also. You know the ratio of oxygen and nitrogen in the air, right? So roughly 100 moles of oxygen will bring 230 moles of nitrogen, right? Because the air composition is almost, remember, 79% nitrogen and 21% oxygen. Okay, so that many times, almost 2.5 times you are making, nitrogen is coming along with the oxygen. Okay, this enters the sulfur burner. Now, what is the product? Product is sulfur combined with oxygen to form sulfur dioxide. You form 100 moles of sulfur dioxide, but 230 moles of nitrogen bar aa raha hai. Then you put to a separator because I want sulfur dioxide, not nitrogen sulfur dioxide. So I put to a separator where I will remove nitrogen as waste and 100 moles of sulfur dioxide as my product. This means I have allocated air and sulfur to the burner, and I have allocated sulfur dioxide and nitrogen to the separator. This is my allocation. Right? Allocation means kahan rakhu? Where do I keep it? Where do I put it in my process? So this is allocation one. Remember, the burner must be large enough not only to accommodate sulfur and oxygen, but also nitrogen. So you see, if you use air, it is bringing so much nitrogen. So I will have to use a burner size will be more because the air contains nitrogen. The nitrogen volume must be accommodated. Right? Burner size, burner life, burner life using air. This air as input will be better because nitrogen acts as an inert. See, remember, sulfur plus oxygen forming sulfur dioxide is a highly exothermic reaction. Okay, so the heat is produced and nitrogen absorbs some of the heat and protects the burner, right? Protect the refractory lining of the burner. Burner is a combustion space with refractory lining to protect, right? Operating flexibility. Remember, if for some reason little air uh, valve in air has got opened or valve in sulfur got opened, my separation will take care and still I will produce the sulfur dioxide pure. Right? So purity is better, flexibility is also better, right? And looking at it, I find that this is okay. But let's not give up. What if I separate air into oxygen and nitrogen? Right. Let's say I separate air into oxygen and nitrogen and throw away the nitrogen and I enter into my burner only 100 moles of oxygen, sorry, sulfur and 100 moles of sulfur, oxygen. Right. So this produces sulfur dioxide. But remember that here the diagram is a little different because this is the third possibility. Actually, we could have made three allocations. In the second allocation, we allocate only sulfur and oxygen to the burner, produce sulfur dioxide. Right? That's as simple as that. But before that, air would have to be separated into oxygen and nitrogen. But remember, separating air into oxygen and nitrogen, the cryogenic, highly costly affair because the properties of nitrogen and oxygen are very close. Separation become costly. Okay, so assume we had that alternative also. We allocated sulfur 100 moles and only oxygen 100 moles to the burner, in which case the burner size will be smaller, but the burner life will be less because there is no nitrogen available to act as inert and protect the burner. So sulfur dioxide comes out of the product. But in a way, remember that sulfur dioxide is also an inert material. Sulfur dioxide does not combine with oxygen to form sulfur trioxide unless a catalyst is present. Sulfur plus oxygen forming sulfur dioxide is a happy to ready to go reaction, whereas the sulfur dioxide with oxygen can form sulfur trioxide only in the presence of some platinum vanadium catalyst, which we will be seeing in the manufacture of sulfuric acid. Okay, so one way to overcome the inert protecting my burner is if I can recycle some SO2 back to the burner and SO2 acts as an inert material, right, and protect my burner. Okay, and so what do I do? I get product. My product comes out, and by cooling the product, because the product sulfur dioxide is very hot, right? Because the exothermic reaction, and the product sulfur dioxide I cool. I take 100 moles as my product, remaining 230 moles of sulfur dioxide. I recycle it back to the burner, which actually in this case the sulfur dioxide is replicating the role of what nitrogen did when we use air. Okay, but if you compare these two processes, in this process there is no separation after the main process, right? There is only cooling. So the any impurity in sulfur dioxide cannot be captured. But whereas here there is a separator, so the purity of sulfur dioxide will be higher, right? So flexibility. See, remember, if sulfur and oxygen slightly excess quantity come, then it will contaminate the product sulfur dioxide, right? So many problems are there and the costly separation. So if I look at, see, unless I am going to put up this allocation 2 in a plant which is using nitrogen and has surplus oxygen, then this will be better for me because I'm literally getting oxygen from the air separation plant, and that plant uses nitrogen. So by looking at a standalone basis, allocation 1 is superior to allocation 2. Then comes separation task selection. Okay. Now remember, as soon as we did reaction path synthesis, we got several reactions. Like for example, for sulfur dioxide, we had at least 4 options: burning sulfur, roasting pyrite, combustion of high sulfur coal, and hydrogen sulfide. We picked up burning sulfur. So reaction path gives you many alternatives. We pick up one. And the reaction path selected leads to many allocation. We just picked sulfur and oxygen and we got 2 allocation. Right. In fact, we had 3. The second and third we have combined. Right. Sulfur dioxide, which is being used as an inert material. Right. So we got multiple. Now remember, now comes to separation. Now the third job in designing a flow sheet is how to choose the separation task. Because once you do species allocation, this species allocation involves separation of sulfur dioxide and nitrogen. This species allocation involves separation of nitrogen and oxygen, which is easier. Remember that this is tougher, and nitrogen and SO2, they have huge difference in the boiling point, so separation will be easier. Okay. Separation task selection. This we will be doing it on what is known as heuristics based. Heuristics are nothing but thumb rules by which we will be doing it. I am listing 9 heuristics. We will take up them in detail in the next lecture because we won't be able to do it. Right. I am just reading it out of the many differences that may exist between the source and destination of a stream. Source is starting point, destination is the ending point. Of the many differences which may be there between the source and the destination, difference involving composition dominate. Because the source tree may have some species, the destination tree may have some species, and the composition difference is what will determine the separation task. Then, when possible, reduce the separation load by stream splitting and blending. Remember, cost of separation depends upon the quantity separated, right? So if I can reduce the separation load, I am reducing the separation cost, right? So if I have to say separate 100 tons, and if I can manage by separating 50 tons, then I have reduced the separation cost by half. Aim to separate the most plentiful components first, right? Out of various species, some species may be more in number than the others. So the more plentiful must be removed first. Because remember that I have to have a series of separation, and if I have, say, 3 components, one of them is plentiful, other 2 are in small quantities. I need at least to separate 3 components, I need 2 separators. In one separator, I cannot separate 3 components. So because I can exploit a property difference at only one at a time, not multiple. Okay. So however, for 3 components, a mixture of 3 components, I have to separate ABC into A, B, and C. Right? Let's say out of this, A is more plentiful as compared to B and C in quantity. So if I remove A first, then my next separator will have less load, which is the logic behind more plentiful must be removed first. Remove corrosive and hazardous material early. If one of my species is corrosive, hazardous, or explosive, I must remove it as early as possible so that the remaining separations are comfortable. If a separation is difficult, then I should do it last. Right? So plentiful first, separation difficult last, and don't bring any foreign species for separation. If you bring it, remove it as early as possible. Avoid excursions in temperature and pressure. Mean don't deviate much from ambient conditions, but if required, then you go high pressure, high temperature than low pressure, low temperature. The reason you should be knowing, we'll discuss in the next lecture. In distillation, remove the desired product as a distillate. Remember, in distillation, based on the volatility difference, you are separating, right? So the one with lighter boil, with a lower boiling point or higher boiling, comes out on top, and the one with a heavier boiling point comes as a bottom product. So the top product is known as distillate, the bottom product is known as simply bottom, right? So I would prefer the desired product as a distillate. Why? We need to answer. And in distillation, favor removal one by one the more volatile compounds. Right. So these are some of the thumb rules, and we will explain each of the thumb rules in the next lecture. See, thumb rules, these are heuristic means, no, we can't give a lot of mathematical explanation. Remember, remove corrosive and hazardous material early. Well, it's logical, right? I must remove corrosive material. If I have 4 separators and my first separator removes the corrosive or hazardous material, my remaining 3 separators are hassle free. And the most plentiful, if my most plentiful is removed in the first separator, then my load on the subsequent separators are less. And if a separation is difficult, I should do it last, not first. Right? You will ask why, we will explain you why. Okay. So that is it. And let's come back. We will take the remaining things in tomorrow's lecture. Okay. So thank you all. Remember, please, have an open mind in learning this subject, right? One cannot go by memorizing things. One must be logical in doing it, right? Like vinyl chloride monomer, I told you, it can have raw material as ethane, ethylene, or acetylene. Each of them has its own plus minus. Like we took monochlorodecane, we found 3 parts. Sulfur dioxide, we found 4 parts, and each reaction path will lead to different species allocation, and each species allocation will lead to different separation tasks. And once separation tasks are selected, then we do an integration and the process flow sheet is ready. And next class, we will be having the flow sheets ready. Okay. Okay. Bye. Bye.